All right, so today we need to learn about center of mass and how to deal with Newton's second law for a system of particles. All right, so here we go. So first, let's give a definition of center of mass. All right, so this first definition up here I stole from Khan Academy because I needed a simple definition. And they define the center of mass is a position defined relative to an object or a system of objects. It's the average position of all of the parts of the system weighted according to their masses. So it's kind of a weighted average. All right, and then reading this, I was not super happy with it, and so here's the final definition I came up with. It's the average position of all of the matter in an object or a system of particles. Okay, so it's probably easiest to do an example with a system of particles first, and then we'll work up to a full object. All right, so let's do this. Let's do a quick example about how you find the center of mass. All right, so if you're dealing with a system of particles in one dimension, okay, so we're going to look at just a number line at this point. All right, you use a weighted average of the particle's location. I guess I'm missing an apostrophe here, right? So we use a weighted average of the particle's location. So to find x, the position of the center of mass, we're going to use COM to represent center of mass. It's just a weighted average. So you take the mass of each particle multiplied by the position of that particle, and then you add up all of the different particles, and then you divide by the total mass, okay? And if we had multiple dimensions, if we had a y-axis, you'd repeat that same process for the y dimension or the z dimension, okay? So let's do a quick example. So I've got this number line here, right? So let's suppose that on a number line, maybe we put a 6 kilogram object here at a position of -4, and maybe over here at a position of 3, maybe we put a 2 kilogram object there. All right, and I want to find the center of mass, the average position of all of the matter in the system. Okay, well, you just use the equation there. So the position of our center of mass is the mass of our first particle, which is 6 kilograms, times its position, which is -4. Let's assume these are meters, plus the mass of the second particle, 2 kilograms, times its position, 3 meters, divided by our total mass, right? So let's see, our total mass is just 6 kilograms plus 2 kilograms. So when you multiply the top, let's see, you get -24 plus 6, so you get -18 kilogram meters, divided by, on the bottom, we've got 8 kilograms. So when you divide this, you get -2.25 meters. So that means that my average location of my mass is over here at -2.25 meters. Okay, notice that's the position. Okay, so right there. Okay, now notice it makes a little more sense that it would be closer to the 6 kilogram, right? Because in terms of our weighted average, the 6 kilograms sort of matters more, right? Yeah. All right. Now, the other thing that is definitely worth noting is this. The choice of where you set your coordinate system doesn't affect the location of the center of mass. Okay? In other words, when I started this problem, we already had our number system set up, right? But basically what we've got here is we've got a 6 kilogram thing that is 7 meters away from a 2 kilogram thing, right? And just to make sure you're clear with that, look, it's 1, 2, 3, 4, 5, 6, 7 meters, right? So the other way we could have done this is we could have said, all right, well, so I've got this coordinate system. I've got a 6 kilogram thing here, and I've got a 2 kilogram thing here, right? And we want to find the center of mass. So let's make our own number system. Let's call this a position of 0, and then we'll just go 1, 2, 3, 4, 5, 6, 7, and do our weighted average again. Okay? So if you do that, watch what happens. Oh, stupid smartboard. You know what? I gotta exit out of full screen. It's gonna drive me nuts. All right. Damn it. I mean, darn it. All right. So let's do our weighted average again. Oh my gosh. Here we go. Oh. I'm sorry. All right, let's do our weighted average. Just use the mouse. Okay. So now let's do our weighted average again. So the position of our center of mass is the mass of object 1 times the position of object 1 plus the mass of object 2 times the position of object 2 all over mass 1 plus mass 2, which for us, well, let's see, mass 1 is 6 kilograms times the position is now 0 plus mass 2 is 2 kilograms times its position, which is 7 meters. Divided by our total mass, which is 6 kilograms plus 2 kilograms. So this gives us 14 kilogram meters over 8 kilograms. And if you divide 14 by 8, that's 1 6/8. So that's what, 1.75 meters, right? But that's not the same number I got before. But what I want you to understand is it's still describing the same position. Think about where a position of 1.75 would be. That would be 1.75, so right here. So 1.75 meters to the right of our 6 kilogram thing, right? So if I scroll up, when we did it the first time, our 6 kilogram thing was right here. And notice it is 1.75 meters over. So it's still describing the same geometric location in space. It's just assigning it a different, number because we chose a different origin. Okay? So that is how you calculate the center of mass for a system of particles. Okay? It's just a weighted average. The smartboard is going to kill me today. All right, now, for objects, the problem is your objects have not an infinite number of particles, but a super gigundous number of particles, right? Like if you wanted to find the center of mass of, a meter stick, a meter stick has a bazillion molecules in it, right? And so basically what you're doing is you're repeating the process for all of the particles, which becomes cumbersome, right? And so it basically boils down to, so you're summing up mass times position for all of the particles in the object, all right, and then dividing by the total mass of all of the particles, all right? So this, hopefully, those of you who are in calculus are now thinking, oh, this looks like an integral. So this sort of infinite-ish sum is an integral, all right? And the total mass of all of the particles is simply the mass of the object, all right? So I will usually use capital M to represent the total mass of the object, okay? All right, so eventually here in the video here, we'll do an example here where we have to integrate. But before we do, let's look at a couple more simple examples, all right? Usually, most of the objects that we're going to deal with are going to have a basically a uniform density, so that the mass of any one chunk is the same as the mass of any other chunk of the same size. And there will be at least some symmetry, so you can simply find the midpoint, all right? So here's a real simple example, all right? So suppose we're trying to find the center of mass of a uniform 70-gram meter stick that has a 200-gram mass attached to the 10-centimeter mark, all right? So here's the deal. So here is our meter stick. So here's the... 10, 20, 30, etc., 50, 60, 70, 80, 90, 100. Okay, so what we've got is we've got a 70 kilogram meter stick, so the mass of the stick is 70 grams, all right? And then what we're going to do is we're going to take a 200-gram mass and attach it right there. 200 grams. Okay, and so what we want to do is we want to find the center of mass of this whole thing. All right, so what we're going to do is this. So the meter stick, because it's uniform, its center of mass is simply going to be at the 50 centimeter mark, okay? So what we can do is, instead of thinking of the meter stick as 100 centimeters worth of particles spread out over that length, we can treat it as an object with all of its mass located right at its center of mass, okay? So the mass of the stick is 70 grams, okay, because it's uniform. And now we can find the center mass. We're basically treating the meter stick as a particle located at the 50 centimeter mark, and then you've got this 200 gram mass at the 10 centimeter mark. So the position of our center of mass is, well, it's the mass of the 200 gram thing times its position, which is 10 centimeters, plus the mass of the stick, 70 grams, times its position, 50 centimeters, divided by the total mass, which is 270 grams, right? And find your position. So if you solve that, you get 20.4. Sure I did that right. Yeah. So this gives you 20.4 centimeters. So that means the center of mass of this stick and mass system is right here at the 20.4 centimeter mark. Okay? The big thing I want you to see from that example, though, is that you can treat a solid object as a particle located at its center of mass. All right? And so this can get even more complicated. All right? Suppose we've got some crazy shape like this. Right? So we've got this plate, but it's got this little like chunk taken out, right? Okay? And so we want to find the x and y coordinates of the center of mass. Okay? So first of all, let's take a look at the y coordinate of the center of mass of this plate. So the y coordinate is telling us how far up or down our center of mass is. Well, notice it's symmetric about the x-axis, right? So there's just as much mass evenly distributed, right? Not only is it the same amount of mass, but, you know, so this particle corresponds to this particle corresponds to this particle, right? So it's completely symmetric about the x-axis, and so that means that our center of mass has to lie along that line of symmetry, okay? So the position vertically of our center of mass is 0. Now, horizontally, it's a little bit more complicated, right? So horizontally, it's not symmetric, right? And you can see there's no way that I can draw any line here to find a line of symmetry, okay? So what we're going to do is we're going to break the mass up into 3 chunks. We're going to have this top chunk. We're going to have a bottom chunk. I'm sorry, a middle chunk and a bottom chunk, right? Okay? And since it's uniform, I'm kind of looking at it and thinking, all right, well, so this top chunk is 3 squares, the middle chunk is 2 squares, and the bottom chunk is 3 squares, right? So that means this guy has a mass of 3m for some amount of mass. This guy has a mass of 2m for some amount of mass. And this guy is back to 3m for some amount of mass, right? So what I'm going to do is I'm going to find the center of mass of each of those 3 rectangles, okay? Well, the top one is symmetrical. So what do we want to, how do we want to do this? It's like 3 blocks wide, right? And so our center mass should be right at the center, right? Okay, same thing for the bottom block. The bottom block is the center mass right at the center. And this middle block, well, shoot, it's got a center of mass that's like right here, right? So it looks to me, based on the drawing, that looks like that's D, right? Okay, so our x center of mass is, well, let's see, the mass of that top particle is 3m times its center of mass is at 0. The mass of the middle block is 2m, and its center of mass is at, make sure you guys followed how I did this. Notice the problem tells us this distance here is d. And so this is just 1d over, right? So negative d. All right. And then that bottom chunk is the same as the top chunk. So that's another, oh no. That's another 3m times 0 all over our total mass, which is 8m, right? 3 plus 2 plus 3. So worth noting here, notice the units that you use to measure your mass are somewhat arbitrary, right? There's no reason why I need to use kilograms, because they're going to cancel out anyway, okay? So, you know, here what I did is I just said, all right, well, let's call the mass of one of these little rectangles here, let's call that m, okay? So if you didn't follow that, that's how I did that. All right, so let's see. So if we simplify this, let's see, these guys go away. And so the m's here cancel, so we're looking at negative d over 4. Okay, so that means that my center of mass is at negative d over 4, comma 0. All right, and I guess the problem tells us that d is 1 meter, but all right, so that is one way of doing this. Okay, again, notice it's about breaking it up into uniform symmetric shapes and finding the center of mass of each chunk, okay? All right, so let's do this another way. So what we did here was we did this by a process that I guess we would call addition, right? Like we looked at the chunk, or sorry, we looked at the block as the sum of 1 plus 2 plus 3, right? We added up those 3 chunks, right? Okay, another way we can do it is by subtraction. Okay, so let's do it this way. It's the exact same problem, but I'm going to solve it a different way. All right, so this whole thing, if it didn't have a hole cut out, again, kind of breaking it up into, you know, little rectangles like this, that whole thing, if it didn't have the chunk cut out, would have a mass of 9m, right? There's 9 little rectangles then, right? And its center of mass would be, you know, dead center, right? Okay, so, well, so I guess real quick, so our y center of mass is still 0, right? For the same reason before. So all we need to worry about now is our x center of mass, right? Okay, so for the whole rectangle, our mass is 9m. So the mass of the whole, let's do that, W-H-O-L-E, all right? And it has a center of mass. The center of mass of the whole thing would be right at the origin, right? So that's if we didn't have the chunk taken out, okay? Now, let's do this. Let's figure out what's going on with the chunk. Well, the chunk would have a center of mass that's right here, right? So that looks like it's 2d over. So its center of mass, so shoot, the position of, shoot, I hate the word, hole and hole. There's a hole here, there's a hole in the hole, so I'm trying to figure out what I'm going to call this. Let's call it M for missing. So the position of the missing thing is right at the center of that, so we decided that was a position of 2d, right? And what's the mass of the missing thing? Well, that's one chunk, right? So the mass of the missing thing is one chunk, but let's call it negative because it's missing, right? We're missing 1 unit of mass, okay? So here we go. Let's find our center of mass. Oops. Why does this keep doing this? All right, so the position of our center of mass, oops. The position of our center of mass is the mass of the whole times the position of the whole plus the mass of the missing bit times the position of the missing bit all over the mass of the whole plus the mass of the missing bit. So the mass of the whole is 9m times its position is 0 plus the mass of the missing bit is negative m times its position is 2d all over our total mass, which is 9m minus m. And so once again, you get negative 2md over 8m gives you negative 1/4 d again, just like we had before. Okay? So, this was interesting. I don't know that this comes up a ton, to be honest, but it was kind of a slick solution. And so I felt like I should share it. All right, so now here's the deal. This is going to be, there'll be a learning curve here, let's say, all right? Now, what if the density isn't uniform, right? Everything that we did so far had uniform density, right? Our steel plate was uniform. Our meter stick was uniform, okay? So that means that, you know, the mass of any 1 centimeter of our meter stick is the same. The mass of any one chunk of our block is the same. Okay, so everything that I've done so far relied on the fact that it was uniform. But what if it's not? All right? So here we've got a thin rod whose density changes along its length. All right? So we can talk about what's called linear density. Lambda is what we call linear density. It is mass per unit length. So lambda is mass per unit length. Okay, but it's changing, right? The density changes. So for us, it's really right? Or I guess since we're using an x-axis, let me use dx instead of dl. Oh, shoot. All right, so it's if you take a very small mass and divide it by the very small length of that mass, that's your linear density at that point. Okay? So here we've got a rod that's got a linear density of 0.8x. Okay? So what does that mean? I guess we should talk about that. So what it's telling us is that our linear density at the origin is 0. Okay? So there's no mass located right at the origin. But the farther you get from the origin, the more dense your material becomes. Okay? So you can kind of picture this. If this is our number line with our origin, you can kind of picture a thing that's getting increasingly thick linearly as you go. All right? So the idea is mass of 0, right? Here, your mass is going to be a little bigger, right? Over here, your mass is going to be bigger. Over here, your mass is going to be bigger, right? So it's getting increasingly massive as you go out, okay? Any individual, you know, dx has an increasing dm, right? So here we've got a small dm, bigger dm, right? So your mass gets bigger the farther you get from the origin, okay? All right, so how do we deal with this? So we want to find the center of mass of this rod, okay? So let me clear up the board a little bit here. So we've got this rod that's got this linear density, 0.8x, all right? We're going to try to find the center of mass of the rod if the rod is 1.5 meters long. Okay, so to do that, we've got to go back to this integral. All right, so remember, this is basically the sum of mass times position of all of the particles divided by the total mass. Okay, so this is going to be weird the first time you see it, but the nice thing is once you learn how to do one of these, they're all the same thing. Okay, so let's run through this. So there are 2 tricks to this. So there are 2 tricks to this. So first of all, we got to do this. We know that our linear density is, for this problem, 0.8x. And we also know that linear density is the ratio of mass per unit length, right? So if we set these 2 things equal to each other, we get this. 0.8x equals dm dx. All right, and so this is a little bit sloppy, but it turns out that calculusly speaking, it works. I'm going to multiply both sides by dx, and I get this, 0.8x, dx equals dm. Okay, so this is the first thing that I need to be aware of. All right, we're going to use that for a substitution. Okay. So, sorry, just thinking about how I want to go about this. All right, so let's figure out the top half of this integral. Let's figure out the top half of the integral. Okay, so what we want to do is we want to find the integral of x with respect to mass. Okay, so what this really means is you want to integrate across the total mass of the thing. So you want to start at a mass of 0 and keep integrating until you get to the full mass of the object. Notice that's a capital M. This is a lowercase m. Okay? Well, so what we're going to do is we're going to use this substitution. Okay? Oops. Smartboard. All right, so this becomes the integral of x times, I'm going to replace dm with this. All right, but now, because we're integrating dx, we don't want to integrate according to the mass, we want to integrate according to the length, right? So we need to start at a position of 0 and keep integrating until we've gotten the whole mass, right? And that occurs at 1.5 meters, right? Because that is how long the rod was, right? Because it is 1.5 meters long, right? Okay, so all right. So now this basically just becomes, I don't want to say simple calculus because it's calculus, but it's simple calculus, all right? So let's see. So x times 0.8x is 0.8x squared, right? So now I'm integrating from 0 to 1.5, 0.8x squared dx. So what do you have to take the derivative of to get 0.8x squared? Oh, well, that's 0.8 over 3x cubed. And then I want to evaluate between 0 and 1.5, right? Oh, cool. So I can do that. So grab your calculator. And let's see, what do we get? 0.8 divided by 3 times 1.5 cubed. And so this gives you 0.9. And the units are going to be, well, it's x is meters, mass is kilograms. So this is kilogram meters. Okay, so that's the top of the integral. Okay? Now, we got to do the bottom of the integral. So the bottom of the integral seems like it's going to be, like, how do we get the total mass of this thing? So we're going to use a little bit of a little calculus trick, right? So what we're going to do is this. So we're trying to find the total mass of the thing. So here's our trick. The total mass of the thing, turns out it's the same as, and it's weird that you need to make this complicated, right? It should just be like, well, what's the mass of the thing? We don't know. All we know is the length of it, right? And the density, right? So it turns out that the mass is equal to the integral of dm from 0 to m, right? So think about why this is true. So what's the integral of x dx? Oh, let's do this. What's the integral of 2 dx? Oh, well, that would be 2x, right? Oh, so that means the integral of dx is just x, right? So the integral of dm is just m, evaluated between 0 and capital M. Oh, that's m. Aha. Ooh, good. All right, so why do we care? All right, well, this is going to allow us to find our mass. So we're going to integrate from 0 to m, dm. And remember, before we had figured out that dm was somewhere on my screen. We've got it up here, right? We know dm is 0.8x dx. So this becomes the integral. I'm going to replace dm with 0.8x dx, right? Oh, but now we're integrating with respect to position, so my position needs to go from 0 to 1.5 again, because that's how long the rod was. Oh, and then we just integrate this. What's the integral of 0.8x? that's 0.4x squared, right? From 0 to 1.5. So plug in your numbers. So grab your calculator. Do you have this written down? Why am I doing it with my calculator? I don't know. And so this gives you, oh, this also gives you 0.9, which is an unfortunate coincidence. But this time it's just meters, just kilograms, right? Okay. So finally I can find the position of my center of mass. So the position of the center of mass is the first number we got, 0.9 kilogram meters divided by 0.9 kilograms gives us 1 meter. Okay? So you will see problems like this. There's one like this on the homework. They are all solved using those exact same steps. All right? The only difference is going to be, the only things I can change on you are the length of the rod and this linear density. All right? The linear density will always be some constant times x, or maybe some constant times x squared, or some constant times x cubed, but it'll always be a monomial, okay? And then you just follow this process, okay? All right, how long is my video so far? Very long, it is a half an hour. We are almost done. Okay, so last thing, Newton's second law for a system of particles. So the center of mass, the motion of the center of mass will continue unaffected by forces that are internal to a system. In other words, well, I'll do an example here. But so the only way that the center of mass, the motion of the center of mass will accelerate is if there is an external force on the system, okay? Which shouldn't be surprising, right? Similar to when we did systems of objects, all right? So the motion of a system's center of mass follows Newton's second law, all right? So the net force on the system is equal to the total mass of the system times the acceleration of the center of mass, okay? And, you know, obviously, or maybe not obviously, but, you know, you can break it up by components. It's true along all three axes, okay? So, a couple things to remember. Your net force is the sum of all external forces, okay? If our system is composed of two objects, we don't care about the force of the two objects pushing each other. All right, capital M is the total mass, which is assumed to be constant, the total mass of the closed system. And then A is this acceleration of the center of mass, okay? So, a simple example of this, if you throw like a bowling pin or something, or a baseball bat, as it's flying through the air, it flips around and around, and I'll attach a video here at the end. But so the idea is, when you throw a bowling pin or a baseball bat, it flips around in the air, but the path that the center of mass follows is still a nice, simple path, because the net force on the system is just the force of gravity on the system, right? Okay? And so while the particles follow a very complex path, the center of mass follows a very predictable one, okay? All right, so that then brings up the question of how do you find the center of, no, sorry. Let's see, we already talked about all this, right? Do we need to say anything here? No, that's all kind of the same thing. So let's talk about how to find the velocity of the center of mass. So it's pretty straightforward, right? Like, check it out. Here's our equation for position of center of mass. So if we take the derivative of this with respect to time, it gives us this. It's the exact same thing. It's still a weighted average. All right. And similarly, if you ever wanted to find the acceleration of the center of mass, it's also a weighted average. M1 times the acceleration of the first particle plus M2 times the acceleration of the second particle, all divided by your total mass. Okay? So let's do a quick example. All right, so here we've got two skaters. Oops. Two skaters on frictionless ice hold on to opposite ends of a pole of negligible mass. An axis runs along it with the origin at the center of mass of the two-skater system. One skater, Fred, weighs twice as much as the other skater, Ethel. So here is our pole. Here's Fred. Here's Ethel. Let's see. Fred has twice the mass, so let's give her a mass of m, and we'll give this a mass of 2m. Hello. So the idea is when they're pulling each other, this is an internal force, right? Fred is pulling Ethel this way, Ethel is pulling Fred that way. That means the net force on our system is, in fact, 0, which means that the acceleration of our system is 0, which means that the displacement of our center of mass is 0. So the problem told us that the origin is where our center of mass was. So as they pull together, when they eventually meet, they have to meet at that center of mass. Okay, because our center of mass can't move because the net force on our system is 0. Okay, now it doesn't matter who pulls who here, right? Because of the third law, right? If Ethel pulls Fred or Fred pulls Ethel, there's always that reaction force at the same time. How you doing, Jeevan? I'm making a video. It's very exciting, isn't it? All right, so last example. All right, I think we can get this last example in here in 3 minutes. Okay, so if I can figure out how to use the computer, we can. All right, so here we've got a two-object system. We've got an automobile. Oops, I said we've got an automobile and a truck. Okay, and they're both driving along. So the 1,000 kilogram automobile is at rest at a traffic signal. At the instant the light turns green, the automobile starts to move with an acceleration of 4 meters a second squared. So let's write down all the stuff we know. Oh my gosh. Let's write down all the stuff we know for the automobile. All right, well, let's see. Its initial position is 0. It is at rest initially. It is going to accelerate at 4 meters per second squared. Okay, meanwhile, our truck, I forgot to write down the mass. Shoot. So much for finishing this in under 3 minutes. Mass of the automobile was 1,000 kilograms. All right, over here, the truck. It's got a starting position of 0, right? Because at the same instant, the 3,000 kilogram truck traveling at a constant speed of 8 meters a second overtakes and passes the automobile. So the mass of the truck is 3,000 kilograms. It's got an initial velocity of 8 meters a second and an acceleration of 0. Okay, and so question A wants us to know how far the center of mass moves in 5 seconds. And what's the speed of the center of mass then? All right, so there are 2 ways we can do this. All right, so option 1 would be to treat the automobile and the truck independently, right? So we could find the displacement for the automobile by doing 1/2 AT squared plus VIT. And that would give you a number that I've written over here somewhere. All right, so if you plug in your numbers just using regular old kinematics equations, you get 50 meters. And similarly, we can find our final velocity by doing VI plus AT, and you get 20 meters a second. All right, so that's everything for the automobile. All right, let's repeat the same process for the truck. The truck is a little bit easier, right, because the velocity is constant. So, oops, I forgot to write our time. Time for all of this is 5 seconds. All right, so the displacement for the truck is, well, the velocity is constant. So just 8 times 5, that gives us 40 meters. And our final velocity, well, it's constant, so it's still 8 meters a second, right? Okay, so since both of our objects began at rest, we can find the final position of our center of mass. So let's find the position of the center of mass final. Well, that's the position of the car times the mass of the car plus the position of the truck times the mass of the truck over the mass of the car plus the mass of the truck. So the final position of the car was 50, mass of the car is 1,000, position of the truck is 40, mass of the truck is 3,000, and our total mass is 4,000. So plug that into your calculatrix, and you will get Clearly not 22.5. What's that give you? Gives you 42.5. Sorry, I written it down wrong in my notes. 42.5 meters. And similarly, we can find the velocity of the center of mass by doing the velocity of the car times the mass of the car plus the velocity of the truck, mass of the truck over the total mass. And it gives you, oops. Let me do this. Nope. Okay, so the velocity of the car at the end was 20. Mass of the car is 1,000. Velocity of the truck is 8. Mass of the truck is 3,000. All divided by 4,000. And this gives you 11 meters per second. Okay, so we can do that, right? What's the point? Well, the point is we could have, if we had wanted to, I don't know why we would want to do this, but we could do it, and it's a thing we need to know how to do, is we could have done all of this just by looking at the center of mass. So let's look at the center of mass. All right, well, the initial position of the center of mass is 0. The total mass is 4,000, right? So we could, if we wanted to, find the initial velocity of the center of mass. So that would be the mass of the truck times the velocity of the truck, or car, sorry. So 1,000 times 0 plus mass of the truck, velocity of the truck, divided by the total mass. And so that gives you 6 meters per second. Okay? We could find the acceleration of the system. So that would be mass of the car, acceleration of the car, mass of truck, acceleration of truck. So you get 1,000 times 4 plus 3,000 times 0, all over 4,000, which gives you what? 1 meter per second squared, is that right? Yes, that clearly gives you 1 meter per second squared, sorry. Okay, and so now we can use our given information here. We know our initial position, we know our initial velocity, we know our acceleration, and our time is 5 seconds. So we can do delta x equals 1/2 at squared plus vit. And so you get 1/2 times 1 times 5 squared plus 6 times 5. And it gives you 42.5 meters again. And similarly, you can find your VF by doing VI plus AT, and you get 11 meters a second. All right, so the point is you can look at the objects individually or just look at the center of mass. Which one's easier? Debatable, but it's a thing you need to know how to do. Now you do.